Hello. Hi everyone. I am Shovik Ghosh. I am a senior CPU design verification engineer currently working at Synopsys. Previous to this, I have here I am working for more than 1 year, 2 months now. Okay. In my previous company, before prior to this, I worked in Intel Technologies, uh, and I worked there for more than 2 years. 2 years, 2 months job experience plus 2 months of internship experience. And prior to that, I did my master's, my MTech from IIT Kanpur. So, and I was a topper there. Okay. I did, uh, I am passionate in VLSI design and digital design. I am working in the verification domain now in VLSI. So I am also interested in front end no, design and verification industry. And in this video, I'll be continuing our walkthrough journey of the problems present in HDLBits. Okay, so let's share the screen and let's start with the session. So, and as always, I'd like to say, if uh, these problems, you should try to solve it yourself first. Okay, and after that, uh, so this problem is solved. Let's move on to the next one. Okay, so these problems you should solve by yourself. And if you're not able to solve it, then see our video solutions. Okay, video walkthroughs. And if you still have doubts, please put it in the comment section. If it's a small doubt, we will solve it on the in the comment section. Otherwise, I'll make a separate video on it. Okay. And if you want a one-on-one counseling or guidance session, or if you want some help or support, please do contact me in my Gmail ID or in my phone number. So both of those information are given below. If you just go, you will find my email ID and phone number. And also, uh, if you like this work, if it is helping you, please support this channel. Okay, please spread the message. You can also contribute if you want. The UPI IDs are given below. So accordingly, you can decide whatever you want to do. You can support in any way you can. Each and every like, share, and subscribe also motivates me a lot to keep going. Okay, so let's start with this problem. Okay, we are continuing our journey in sequential logic, D flip-flops. We have covered D flip-flop, and then we will create 8 D flip-flops. Okay, create 8 D flip-flops. All D flip-flops should be triggered by the positive edge of clock. So in case of D flip-flop, we have learned what we need to do is we need to create a clocked always block. So we need to create an always at the rate. Okay, and then we need to give clock here. So what we do is we give positive edge of clock. Positive edge of clock. Why we give positive edge of clock? Because in a D flip flop, I mean usually a D flip flop gets triggered with a positive edge of clock. Here we will consider positive edge. Okay. It also said that all the D flip flops should be triggered by the positive edge of clock. It said already. So we give positive edge of clock, and then we give begin and end. And then what we need to do is output Q becomes equal to D. Okay, output Q becomes equal to, so it's like less than equal to, that you can see. It is not less than equal to. It says D value goes to Q. It's a non-blocking assignment. So D value is assigned to Q. Okay, at the end of the time step. What does this mean is if I have 10, 20 similar statements like this, all of them will be executed at once, not one after the other. Okay, this is what it means. Okay, so this problem is solved. Uh, let's submit it. So each and every bit of D, which is like 8 bits of D, gets assigned to 8 bits of Q. Okay, status is success. You can see the waveforms here. So whatever is D at the clock positive edge, so next positive edge, the value will change. 9 was here, 9 will come here. So after the positive edge, the value changed to 63. But at the next positive edge, this 63 was not there. So you don't get 63 here, you get D because D was the value which was present when the clock was having the positive edge. Okay. So this is what we can see in the output in case of our output, and in case of this Q, we can see the values are same. So we did the right thing. Okay. So let's move on to the next problem. So if you want a better explanation in in let's say Hindi language or something, you can let me know. I can take a session for you, separate session. Okay. Create 8D flip-flops with active high synchronous reset. With active high synchronous reset. Okay, all D flip-flops. Synchronous reset means the reset works, or when the reset is you know what happens in reset is when reset becomes 0, the circuit is reset, or when the reset is 1, the circuit is reset. Okay, let's say the circuit is it says active high synchronous reset. Active high means when the reset is high, then it will work. Okay, synchronous means when clock is there, then only we will check the reset value. All D flip flop should be triggered at positive edge of clock. So how to do it is we will say always, first always at the rate pause edge of clock, and then what we will do is we will say if, then we will check reset. If there is reset, okay, we need to give a begin and here as well. Then Q equal to 0, output equal to 0, 8 tick B0, 8 tick B0. So I'm saying 8 zeros basically because Q is a 8-bit value. Okay. And else, because I gave if, we need to give else, we can give else, and we need to, if reset is there, we will not go into else. If reset is not there, then we will go into else, and what we will do is for that I'll give begin and end. In the else block, we will say Q equal to D. So 8-bit Q gets value from 8-bit D. D is an 8-bit value. Okay. So just let's submit this problem. See, success. You can see the waveform as well. Okay. In case of reference, they don't know what is this value. I just said it's 0. So it's okay. But after that, all of the things are matching. Okay. So let's move on to the next problem. D flip flop with reset value. So what we need to give here is a D flip flop with reset value. Okay. Create 8 D flip flops with active high synchronous reset. The same thing. The flip flop must be reset to 0x34 rather than 0. All flip flops should be triggered by the negative edge of clock. Okay, what we do is it's a synchronous reset, but active high. Okay, so what we do is always at the rate pause edge of clock. Okay, begin. Oh, neg edge of negative edge. It's a negative edge of the clock. Neg edge of clock begin end. If something, if reset begin end, else end. Okay, so this is the structure. Okay, if reset, I am saying if reset because it's active high. So when reset is 1, active high reset, synchronous reset. Synchronous means we check after the clock. We don't say negative edge of clock or positive edge of reset or something like that. So when we do reset, the value we should get is 0x34. Okay. Q. So we will not say 0x34. What we will do is 8 tick hex 34. So this means 8-bit value in hex. What? 34. Okay. This is what it means. And then we say Q less than equal to D. If reset is not there. If reset is not there, then Q equal to D. Clock reset DQ. Okay. Reset clock QQD. Okay. We have given the right values. We have given semicolon. Okay. Begin end. Begin end. Okay. Good. So let's see. As usual, the status is a success. Okay. Now we will have asynchronous reset in the next one. Okay. Create an 8D flip flop with active high asynchronous reset. Asynchronous reset. All D flip flops should be triggered by the positive edge of clock. So we will do always add the rate pause edge of clock begin end, and here also only we have reset as well. Reset positive edge of clock and reset. So when there's a reset, what happens is if reset. So when there's no clock but reset is there, then also this always block gets triggered. If reset begin end else begin end. Okay. This is asynchronous reset. So A reset. Okay. Active high synchronous reset. Active high. So we say check 1. Okay, good. And nothing is written. So if reset Q equal to 0, Q less. I mean this is non-blocking assignment. Q gets 8 tick B0. It's like all zeros. So 8 tick B0, 8 tick B0 is the same. 8 tick B. Okay, so these two are same. So you can say 8 tick B0 or you can say 8 tick B 8 zeros. Or you can also say 8 tick H00 or 8 tick H00. Okay. So as you wish. Now what we can do here is Q gets the value of D. Q gets the value of D when there is no reset. Okay. So let's submit and see what happens. I just have one doubt. So this asynchronous reset, we need to take positive edge or we can just give directly double edge express. That is what I thought. So we need to give positive edge of reset. So we need to, if I give positive edge of clock, we have to give some edge of the other values as well. So if in the always block, one thing is working as a edge, so positive edge or negative edge of clock, other all values should come as edge only, positive edge of reset. Now if we submit, it should work. I had this confusion. I thought of trying it out, so I didn't give the positive edge to see what happens. Okay. And to show you also, because before even the output came, the error came, I said I had one doubt. So, okay, because I studied that. Okay, we should give positive edge. Anyways, that's good. I can see the values matching. I can see it's a success. So our solution is correct. You can check it here. Okay. So if I give positive edge of clock, all the other sensitivity list. So anything that I put inside the always at the rate, it is called sensitivity list. So when any of these values change, we go inside. So positive edge of clock. So this clock, I am checking the positive edge of this signal. If I do that, I have to see the edges only of other signals, either positive edge or negative edge or something. Okay. Positive edge of reset. It's not when reset equal to 1. It's when reset becomes 1. When reset becomes 1. Okay. We will not check at negative edge of reset. It's not like whenever reset changes. Okay. So, okay, great. If I want this circuit to get triggered at both positive edge of reset and negative edge of reset, at every change of reset, then we should write negative edge of reset as well, like this negative edge of reset. Okay. But currently we are not checking negative edge of reset. We are saying when there is this reset going from 0 to 1, whenever the reset goes from 0 to 1, we reset the signal. But when reset gets deactivated, so when reset becomes 1 to 0, we don't immediately say q equal to d. We wait for the positive edge of clock. Okay. Then I see that reset is not there. Then I say q should be equal to d. Okay. Whenever the reset goes low, whenever the reset goes high, we immediately make it 0. We don't wait for the clock. But when reset goes low, we don't immediately take q equal to d. We don't do that. Okay. What we do is we say when clock comes, now we will take the input. Whenever clock comes, we will accept the input. When reset is there, even if clock comes, it becomes reset only. But when reset is not there, when clock comes, we don't go into this if condition. We take the value of d. Okay. So great. Let's move on to the next problem. Create 16 D flip-flops. It is sometimes useful to only modify parts of a group flip-flops. The byte enable inputs control whether each byte of the 16 registers should be written to on that cycle. Byte enable 1 controls byte enable 1 controls the upper byte. Byte enable 0 controls the lower byte. Hmm. Okay, let's do this and let's stop. I am feeling actually a bit tired. Anyways, let it be. Create 16-bit flip-flops. Okay, so what we need to do is we need to create a 16-bit flip-flop. So we have 16-bit D, 16-bit Q. Okay, it's sometimes useful to modify parts of a enable inputs control whether each byte of the 16. Okay, so what we will do is we have a reset as well. So synchronous, active low, active low. Okay, always at the rate passage of clock. What it said? Synchronous. So it's synced with the clock. Okay, good. Begin it. If not of reset, because it said active low. When reset becomes 0, it works. When reset comes back to 1, it's normal circuit. When reset equal to 0, then we should make the output as 0. So useful to only modify parts of a group of flip-flops. So it's sometimes useful to only modify some parts of a group of flip-flops. So it's like sometimes it is useful not to modify the whole flip-flop, but to modify only part of the flip-flop. The byte enable inputs control whether each byte of 16 bits should be written on to that cycle. Okay. All D flip-flop should be triggered by the positive edge of clock. So when I do positive edge of clock, if there is no reset, what we do is we say Q equal to D, sorry, Q equal to 0. Whenever there's a reset, immediately make it 0. Okay. Else elif ELS I else if no. Let me check the structure. If else if in Verilog. Let me check if it is directly there or we have to make a nested if. So end else if. So we have else if. Else if. Okay, that is how we need to say. We can also do it like this. End else if this. So if reset, not if not reset, then make equal to 0. Okay. Else if the reset is not the case, or we should say else begin. If so, it's like if reset is not there, we come into else. We'll make it this way only because I kind of like this way of writing. Begin and Okay. Okay. What I'm doing is I'm saying else means when reset is not there, basically there's no reset condition, we will check if the lower byte is enabled, we will take the lower byte value, lower byte. So it's like byte enable. Okay, byte enable 1 controls 15 to 18. If byte enable 1 is active, okay, queue of 15 down to 8 equal to D 15 down to 8, and we give this sign to say it's a non-blocking assignment, and there's no else. Okay, I am saying if both are true, then we take both the values. Okay, so we say 7 down to 0, 7 down to 0. So I am saying if byte enable 1 is there, take this value. If byte enable 0 is there, okay, then take this value. If both are there, both if will be triggered, both values will be taken. Okay, triggered with positive edge of clock. Okay, a byte enable control whether each byte of should be written on to that cycle. Upper byte 0 controls the lower byte. Okay, so okay, if either value is not there or something, it holds the previous value. Okay, I hope I gave semicolon and all everything. Okay, if else begin and okay, great. So it should be a success. Okay, reset is not declared, so there's a reset n. I don't know why they change the name every time and then see it's a success. I just mistakenly took the name of reset as reset, but it's reset n. So otherwise, the logic is fine. Okay. So okay, let's move on to the next problem. Let's see what is there. Let's solve it. Okay. Implement the following circuit. So you have to implement this circuit. What we will do here is note that it is a latch, so a quarter surrounding or input latch is expected. Okay. So when there's enable equal to D, enable. That's always at the rate star begin and we'll say if enable enable begin and okay, I am saying q equal to D, q equal to D. Okay. We should not use non-blocking here because there's no clock involved. So we should use q equal to D. not equal to q equal to d. Q gets the value of d assigned to it. Okay, d gets assigned to q. We don't give non-blocking this less than equal to because there's no clock involved. Okay, it's not like it had to wait for the clock. When clock comes immediately it can do, otherwise it can't take the value. It's not like that. Okay, so we can give q equal to d in this case. There'll be an inferred latch, but it's okay. Let's see what it gives. Okay. Q is the output. Great. Other two are input. Put ENA. Okay, D. Okay. See, it's a success. It will say latch is inferred. Inferred latch. What it means is when there is enable, Q gets the value of D. When enable is 0, what happens? It's not mentioned. That means when enable is not there, Q holds its previous value. And that is what latch is. It latches the previous value till it gets a new value. So it's like if enable is there, D is given to the output Q. D value is assigned to the output Q. If enable is not there, then there's no then condition. There's if, but there's no then. In that case, it actually means an inferred logic. I mean, it actually says it's a latch basically. Okay, it indirectly says it's a latch. Okay, that it was what it says, inferred latch. Okay, line number 7. If is there, else is not there. Corresponding else is not there. Okay, so okay, let's move on to the next problem. So whenever else is not there, we have to assume that okay, nothing changes. If this, if enable is there, output changes. Output becomes equal to D. What if enable is not there? We didn't say anything. Okay, so that's what. Implement the following circuit. Here we see a triggered clock. Okay, clock is there, D is there, Q is there. This is asynchronous reset. Asynchronous reset, AR. This asynchronous reset. What is asynchronous reset is when there's a reset, the circuit will get reset. Okay, always at the rate pausage of clock, pausage of reset, begin, end. Okay, this becomes normal. Now I say if reset. Oh, this reset name is AR, asynchronous reset. If AR begin, end. So this is where they are creating the problems. They are changing the names unnecessarily. Else begin, end. So I am saying if there's a reset, if there's the reset, what you do is, if the reset is 1, what you do is you do q equal to 0. Otherwise do q equal to d. Okay, because q is the 1 bit, 1 tick base 0. Okay, you can do 0 also, or you can do 1 tick base 0. Very simple problem. Let's see.
Welcome to Urban Company. This call may be recorded for quality and training purposes.
Okay, wait a minute. I'll share the screen again. Didn't I share the screen before? Okay, that's the case. I'll solve all these problems again for you. Okay. Let me stop here itself. Let me stop here. We will cover in the next class.